Okay, so this is just a brief video about hypothesis testing errors. We've talked about hypothesis testing already, and we talked about it using this analogy of a courtroom where Mr. Null, if you will, was on trial, and we were trying to determine if there was sufficient evidence to reject his claim about the true state of the world, basically the true population mean. And in that little drama, we determined that we would reject the null hypothesis because we had a p-value of less than 0.05, so a probability less than 0.05 that we would observe something as absurd as we did, as extreme as we did, if the null hypothesis is true. So strong evidence against the null hypothesis. But there is this possibility that the null hypothesis could actually be true, and therefore it could be possible to reject a null hypothesis when we actually shouldn't. So, for example, this of course happens in real life. People are sometimes wrongfully convicted of a crime. The evidence is strong enough to reject their claim of innocence, but in reality they were. The true state of the world was they were innocent. So this is what is called a type 1 error, and this is when you reject a null hypothesis. Basically, you get a p-value less than 0.05 and you reject the null hypothesis. But in reality, in true reality, the null hypothesis was true. So maybe the claim is that mu is 100. We find through a sample, we collect a sample, and it's a very extreme sample mean. Different enough from that it's a less than 5% chance that we would observe something that extreme if the null hypothesis were true. But that can still happen, right? There's still a 5% chance. In fact, 5% chance, that means 1 out of 20 times you're going to be getting a sample mean that's that extreme if you were to repeat this multiple times. And so you have a 1 out of 20 chance of rejecting a true null hypothesis. Okay, so the type 1 error rate, therefore, is 5%, using the typical convention of 0.05. So much of the time we're comfortable with that, but we still have to acknowledge that there is that 5% chance that we've made a wrong decision. Okay, so let's say we don't like that. We want to reduce the probability of a type 1 error. What would you do? Well, what you could do is you could set a lower cutoff. You say, okay, I'm not going to go with that typical convention of 0.05. I need a p-value of even lower than that. Okay, it's got to be even more different from mu. We've got to get an x-bar that's even more extreme. And so therefore we'd have to have a p-value, say, of like 0.01 or less than 0.001. Okay, and there are scenarios in which you would want to do this. But maybe you're seeing there could be an issue with this. What if the null hypothesis is in fact false? Okay, and we simply just fail to reject it because we set too stringent of a cutoff. Okay, this is like letting a guilty, in the courtroom analogy, this is like letting a guilty person go free. Okay, so they're kind of two sides of the same coin. We can either we can reduce our probability of a type 1 error, but at the same time we're going to be increasing our probability of what's called a type 2 error, which is failing to reject the null hypothesis when in fact it is false. It should be rejected. Okay, so this is kind of a nice table that kind of lays this all out. Okay, so we have a conclusion from a statistical analysis. Okay, p-value low, reject HO. How low? Well, usually it's 0.05, but we could set it lower or maybe even higher if we wanted. But whatever we set it at, that's what it's set at. And if we get a p-value lower than that cutoff, then we reject the null hypothesis. Okay. Now, these green boxes indicate correct conclusions. Okay. So, and this other axis here is, this other dimension is the true state of the world, or the true state of nature. Okay. So if the null hypothesis is true, and we would say fail to reject the null is more proper language here than just accept the null. But or if the null hypothesis is false. Okay, so if we reject a false thing, that's good, right? We want to reject false null hypotheses. And based on typical cutoffs, this is going to happen most of the time, right? 19 times out of 20 using the typical cutoff of 0.05. However, you may reject the null hypothesis when in fact it's true, so that's a type 1 error. Or you may say the null hypothesis is true and you got a p-value greater than 0.05, so p-value is high, so we didn't reject the null hypothesis. And that was the right call. It was actually true, and so that was the correct conclusion. However, what if we get a p-value, and it doesn't necessarily, just because you get a, or set your cutoff different from 0.05 doesn't mean that a type 2 error can't happen. It could still happen at a p of 0.05, just because you're randomly sampling, right? And you're going to have chance variation from sample to sample. So you could also fail to reject a false null hypothesis. Null hypothesis is false. Mr. Null was guilty, but we let him off. Okay. So this is kind of a silly analogy. Another example. Let's say the null hypothesis is that you're not pregnant. Okay, so a type 1 error would be this scenario. You're pregnant. Rejecting this rejecting a true null hypothesis. This guy's obviously not pregnant, but they rejected the null. And here they failed to reject a true null hypothesis. Okay. We actually have two symbols that are used to depict each of these, or that are used for each of these. Alpha is the probability of type 1 error. Now this is the same alpha that we've talked about before, the cutoff, right? But that makes sense because whatever you set your cutoff as, that's the probability of a type 1 error that you're comfortable with. So if it's 0.05, then you're saying, I'm okay with, 1 out of 20 times this is going to actually come back to bite me, that I actually rejected a true null hypothesis. That's the typical convention. As a researcher, you'll need to decide if that's going to be acceptable or not. And then beta is the symbol that we use for the probability of a type 2 error. Okay. So here's another table that just kind of shows this. Reject HO, fail to reject, true state of the world. So now this is the same table that I showed before, but this is from the textbook, and this just shows where the how we depict each of these with symbols. Okay, so type 2 error, type 1 error, alpha, beta. The correct decision over here, if null hypothesis is true, is 1 minus alpha. So probability of a correct decision when the null hypothesis is true would be 0.95 if we use the typical convention. Okay, and then null hypothesis is, if the null hypothesis is false and we reject it in favor of the alternative, then the probability is 1 minus beta of making that correct decision. Now, just to introduce briefly this term, power, this is called power. We'll talk about this later, but this is something that you want to maximize, right? The probability of making a correct decision. This is what it looks like graphically. Okay, so let's say up here, this is the distribution under the null hypothesis. Okay, so this finger tapping rate is 60. So this is kind of the distribution for healthy participants. Okay, and then if we get something that's less than, if this is a one-tailed test, then this would be like less than 5% of this tail. If it's this extreme, then that's our alpha. Okay, so if you get an X bar that's less than about 52 or so, or no, 48, excuse me, 48 or so, then you'd say we reject the null hypothesis. Okay? But if it's actually true, then this is the probability of making a type 1 error. The area under this curve. Basically, that's if you're kind of throwing darts. 5% of the time you're going to get it here, and that's where you're going to reject a true null hypothesis, because now we're talking about the null hypothesis under the null, or the distribution under the null hypothesis. Okay. Now you can see here's beta, and in this case, remember beta, if we go back, beta, that's when the null hypothesis is false. So now we're in the alternative world, if you will, not the null world, and still if an X bar lands here, then we have rejected the null hypothesis, or we fail to reject a null hypothesis if it's on this side of the line. But in this case, it was false. Okay, so that's another bad decision. Okay, so that's just what it looks like graphically. And just so you know, H1, that's the same as HA. Sometimes they're, that symbol is used instead. Okay, so those are hypothesis testing errors, and some of these concepts will come up later when we talk about power in more depth. So that's it.